Okay, so now that we've covered a little bit more, the different types of cross-validation that we can use in order to basically test the performance of a classifier. Something else that we're interested in doing is, okay, now we know really well, we've covered different performance measures that we can use. We've also covered different cross-validation techniques that we can use. So how can we use those to compare results across classifiers? So there's a package in R called the Caret package, and the Caret package basically what it allows you to do is to run different types of classification techniques and cross validations easily and to be able to easily compare those. Okay, so basically what the Caret package does for you is that it divides your data set into training and testing as you tell it to divide it. Okay, so if you tell Caret, I want to divide my data set into training and testing using repeated subsampling, or using k-folds with 10 folds, or using a data split 80-20, Caret does that, and basically then it runs the classifiers that you tell it to run, and it compares accuracy across those classifiers. And the comparison, it's basically the strongest comparison that you could do across classifiers, because you are certain that the classifiers are being trained and tested on exactly the same subsets of samples. So there's a couple of important functions in the Caret package. Again, as usual, the last slide of this class contains links to the Caret package that you can check for broader information and to understand what other functions are there that you could potentially use or you could be interested in using. But one of the most important functions in the Caret package is basically the train function, right? And in the train function, what you basically do is that you tell Caret to train a model using a specific method, right? So you can tell it to run naive Bayes, support vector machines, random forest, decision tree, whatever you want to run. And you also need to mention the type of cross-validation that you want to use. Okay, do you want to use k-fold, if not cross-validation, whatever you want to use. Okay, and so the way we typically do this, okay, I mean, this is an example of what the train function would look like, right? I mean, this is for the dataset, the iris dataset. Remember, we saw it a while ago. It contains information about the petal size and petal width, I think, for 3 different types of flowers. And the idea here is that you can predict the species based on those width and length measures. And so here what the train function is doing is saying, okay, I want to predict the species using the data in the iris dataset, and I'm going to be using the method that I'm going to be using, the classifier that I'm going to be using is naive Bayes, and the type of cross-validation is one that I call train control. So the TR control parameter allows you to specify the type of cross-validation, and the method parameter allows you to specify the type of classification method that you want to use. Okay, and so typically the TR control, we typically create a separate object specifying the characteristics for that element. And so in our case, the train control object is created using a train control function. Okay, and in this case, the train control function, we're specifying that the method that we want to use, the cross-validation method that we want to use, in this case is k-fold. CV is what the Caret package represents as k-fold, and the number is the number of folds that we want to consider. So we are basically, with this command here, what we are saying is that we want to create a cross-validation that is a 10-fold cross-validation. And then obviously we'll have the predict function in the Caret package that basically allows us to, using the trained model, predict the performance of our classifier over a testing data set. So let's go through a concrete example again. So let's go to our studio. And here what we're going to do is basically create a cross-validation object, specifying that we want to do like the 10-fold cross-validation. We're going to train a model, okay, with that, and basically we're going to use the predict function to predict how well we are doing, but just with one model, without comparing across others. And then we'll see another example where we will be comparing models. So first thing that we do is that we load the Caret library, okay? And then basically we're going to be using the iris dataset. Again, oops, sorry. if you want to see the contents of the Iris dataset, this is what I was talking about before. So we have the species, indicates that it can be 3 different types of species: Setosa, versicolor, and virginica. Okay, and basically what you want to do is classify the species based on length and width, these 2 length and width measures for the petal and the sepal. Okay, this is what we want to classify. Very simple data set, widely used in machine learning. And so, what we're going to do now is basically we want to train a naive-based model to classify these, and we want to use k-fold cross-validation. So the first thing that we do is that we create the train control. We create the cross-validation object in which we specify, using the train control function, the method that we want to use, which in our case is tenfold, and the number of folds. Okay, so what we're saying here is this is an object. Whenever I say train control, I'm going to be referring to the fact that I want to run a tenfold cross-validation. And then we basically train our model. What we want to predict is the species. Okay, that's what we want to predict. And basically what we want to use to predict this is the Iris dataset. And now here is where we specify, the parameter TR control, which is basically, what type of cross-validation you want to run. And we put here the name of the object that we have created. And we also need to specify, what's the method, what's the classifier that we want to use, which in our case is naive Bayes. Okay, and you can check again in the documentation. Species. In the documentation, you can check the different types of methods. Okay, that you can use with Caret, but it's basically, it allows you to use almost all of the methods that we've covered. And the names are very intuitive, right? So SVM is SVM and so on. Okay, and so we have trained the model with tenfold cross-validation, and now what we can do is basically, do some predictions. So we are going to predict using the model that we have trained, and basically the data set that we are going to be using is of the data points that we have and the 4 independent variables that we have, right? So here we are removing basically the label, the species, right? And so, if we want to look at the confusion matrix with the predictions that we gotten from the model and the actual values, what we get is something like this. And what you can see here, basically, okay, here at the top, what you can see is the confusion matrix. So you can see that, we are perfectly identifying all the Setosa. We're also doing very, very well for versicolor and virginica, right? Only 3 samples are incorrectly classified. Okay, so the accuracy is really high, it's 96%, but you can also explore other measures like sensitivity, specificity, positive prediction value, negative prediction value, detection rate, and so on for each class independently, right? So sensitivity and specificity, as you can see for the Setosa class, is 1, because in fact we've done it perfectly. And on the other hand, for versicolor and virginica, there was a small error. So you see the sensitivity going down to 94%, specificity also going down a little bit. Okay, but still very good classifier. Okay, so so far so good, but so far, this is nothing new, right? So this is something that we could already do before, because, we know that there are packages to run naive Bayes. We know that, we can kind of manually do the tenfold cross-validation. So, I would say that so far, what's interesting from the Caret package is that we can use it to determine the type of cross-validation without worrying of doing it ourselves manually, okay? But there's more to the Caret package. And in fact, another interesting feature of the Caret package, as I mentioned before, is the fact that, we can compare across classifiers. We can compare performance results across classifiers.
So let's see how to do that. Imagine that, for example, we want to compare the accuracy of 3 different classifiers. We're going to be working with a naive Bayes classifier, an SVM, and a random forest. Okay, and we want to see how these 3 methods compare for a specific data set in terms of, for example, accuracy. And we also want to use exactly the same cross-validation approach. Let's, for example, say that we are going to train these 3 models using k-fold cross-validation with 10 folds, and that we want to run this 3 times. Okay, so the Caret package will allow us to do this comparison, making sure that the 3 methods are compared across exactly the same training and testing data sets with the same cross-validation approach. Okay. And how do we do this? So besides all the different functions that we have described in the Caret package, there's also another one which is called resamples. And this command allows us to basically, once we have trained 3 different models or n different models, it allows us to compare how these models do in terms of, for example, accuracy and also other metrics that we will see. Specifically, we're going to be looking into an example where we will train these 3 models, naive Bayes, support vector machines, and random forest on the same dataset with the specific cross-validation approach that I have just discussed using the train control function. And we will be looking at how the performance of these 3 methods compare in terms of distribution of the accuracy, both for the median and different quartiles, but also we will be looking at a couple of visualizations with box plots and dot plots for exactly these same figures.
So let's go through that. In this case, I'm going to be using a different example. Okay, so in this case, I'm going to be using an example from, remember that that's also another interesting thing that R has. There's many packages that, as part of the package, they contain data sets so that you can, try the different features that that package has. And I'm going to be using the MLBench library, which contains a very interesting data set with diabetes information for different individuals. So in this case, we're going to be trying to predict whether an individual is diabetic or not based on a set of individual information. So let me load this data, Indians diabetes. Okay, and if we take a look at that, okay, it's basically here, the diabetes column tells us whether, the person is tested positive or negative on diabetes. And then we have a whole set of features. We have 8 different features, whether the person is pregnant or not, which might play a role in, having diabetes, the levels of glucose, pressure, triceps, insulin, body mass, pedigree, and age. Okay, and basically what we're going to do here is predict whether someone is going to have diabetes or not based on, these different features that we have. That's our objective, right? And so, okay, so in this case, we're going to try a different control method. What we want to do is basically what's called repeated k-fold cross-validation. And so in this case, basically, rather than just creating, say, 10 folds and running it 10 times, we want to repeat that 3 times. So we want to create 10 folds, train with 9 of them, test with 1, repeat that 10 times, and then repeat the whole process 3 times. That's what a repeated CV means for the Caret package, right? So we're going to create now a control object, which is basically using the train control function again. The cross-validation method that we are going to be using is repeated CV, okay? And then the number of folds is 10, and the number of repeats that we want to do is 3, okay? That's going to be our control object now. And now what we're going to do is basically train 3 different models. We're going to be training, let me check this, naive Bayes, we're going to be training random forest, and we're going to be training an SVM, okay? And basically then what we'll do is compare the performance for the 3 of them using the Caret package. So in this case, let's set the random seed again. And in this case, what we're going to do is, the naive Bayes model, we're going to use the train function in Caret. What we're going to predict again is the diabetes, right? And the data that we're going to be using is the PIMA Indians diabetes data set. We are going to be using a naive Bayes classifier, and the control object that we're going to be using is the one that we've created called control, okay? So that's our naive Bayes classifier. We are going to do exactly the same thing for random forest, okay? here, don't worry about the warnings. It's basically just that there are some outliers in this data set, and so what it's basically telling you is that the classifier, it's not going to do as well as we would expect it to do. But I mean, it's just a warning, so don't worry about that. If you get the warning, that's fine. We are also going to basically model a random forest, right? So we again use the train function from the carrot package. We want to predict diabetes using the PIMA Indians diabetes dataset. In this case, the method that we are using is random forest, okay? And the control that we are using, again, is the control. And we put verbose to false because otherwise it gives a lot of messages and it would be crazy. And once we get the random forest, we are going to do exactly the same thing for support vector machine, okay? The only change that it's going to have the command line is basically the method that we're using, the classifier that we are using, which is going to be called SVM radial, because we use the radial basis function. We use an RBF kernel for the support vector machine, okay? That's the only difference that we're going to have. And so once we train those three models, we'll use the resamples command. And the resamples command, what you need to do is create a list and say, okay, so these are the X different models that I want to compare. And what the resamples does is that it basically compares the accuracy across the different models that you've run. So the random forest is taking a while, and we are done now. And let's run the support vector machine here. Again, we predict diabetes. The data that we use is the PIMA Indians diabetes. The method that we use in this case is SVM radial, and the control is the control one, the control object that we are using. Okay. Okay, so we wait until the SVM is trained, and again, what I was saying before, for the names of the methods, make sure that you check the package. And so now what we want to do is basically, the beauty of the carrot package that I've been talking about. You can compare performance across classifiers. So for that, we use the command resamples, right? And we create a list with the different models that we want to be using. So we want to be using the naive Bayes, which we've called model MB. We want to be using the random forest, and we want to be using the SVM, right? Which we've called model SVM. And so now what we can do is basically take a look at the summary of those results of that comparison. Let me open this largely. And so what this summary is telling us, the number of resamples is 30. What this means is that we've used 3 times k-fold cross-validation, okay? And here it's basically telling us the median accuracy and the median kappa values for both naive Bayes, random forest, and super vector machines. So if you look at the median values here, you can see that the performance across them is quite similar, but random forest is the one that performs best, okay, with 77% of accuracy. Okay, and so the interesting thing about this comparison is that it's the most accurate comparison that you could have, because in fact, the training and the testing data sets that we're using are the best ones.
To wrap up with this diabetes example, we can also look at visualizations of the results that we just discussed for naive Bayes, super vector machines, and random forests. And so what you have in the next 2 slides are the result of running bwplot and dotplot, these 2 commands with the results data that we have with the output from the 3 different models. And this is just another way of looking into the accuracies that we just discussed in R. Okay, so we can visualize accuracies as box plots or as well as dot representations. What you see here, besides accuracy, you see that we have another metric, which is kappa for each of the 3 classifiers that we have trained. And so kappa, also known as Cohen's kappa, is basically like a classification accuracy, except that it is normalized at the baseline of the random chance on your data set. What this means is that, for example, imagine that you have 2 classes that have a very similar number of data points in each of the 2 classes, right? There's a high probability that you might be getting a correct answer just by random guessing, because you only have two options, because the model only has two options to pick from. And so chances are that the answer might be right just out of randomness, right? Whereas in the case where you have, for example, 10 different classes, it's relatively much harder to randomly guess that's one of the 10 classes, right? And so the fact that you get a class right highly probably means that that's the right label, because the model has learned to identify that pattern rather than out of chance. Okay, and so that's the reason why Cohen's kappa is often used, basically to understand accuracy normalized at that baseline of potential randomness in your model. And it is generally very useful when you have data sets that are imbalanced, because it allows you to compute a normalized accuracy metric that takes into account that imbalance. Something slightly similar to what the F1 score, the micro F1 score that we discussed, does. So if you think, for example, of an imbalanced data set where you have 70% of the samples, say, are class 0, 30% of the samples are class 1, you can achieve 70% accuracy by just predicting all the instances as being class 0, right? And, you will get a very good model when in reality you are performing very poorly for one specific class. And so, this kappa metric allows us to also look into that. And so if we look at these results, what do we see here? So, this is something that we already discussed, right? So we see the three accuracy metrics here. We observe that the median values, okay, and the quartiles, first and third quartile. And what we observe here is, as we discussed, naive Bayes has an accuracy that is slightly better than support vector machines and then random forests, okay, although the results are very similar in around the 70s. However, very interestingly, we observe that the kappa metric is slightly different. The kappa metric, the best value is for the random forests. Then we have naive Bayes, and then support vector machines. Okay, so we see that whereas if we were to look at accuracy, naive Bayes is the best method. When we are looking at kappa metrics, random forests appear to be the best method. Okay, and that makes sense. If you go back to the diabetes data set that we've been using and look at the distribution of positive and negative labels, we have around 500 samples that have a negative diabetes label, and the remaining 268 have a positive. So this means that the data set that we have is largely imbalanced, and so as a result, when we normalize at the baseline of random chance, the results are changing because our data set is imbalanced, right? If we were to have a balanced data set, probably these two metrics could be much more similar. Okay, and so in this case, you have to understand the nature of your data set and the fact that it's imbalanced, and maybe our choice should be more based on the kappa metric rather than on the accuracy metric, and we would, for example, choose random forest or naive Bayes that also performs pretty well as the model to use. And these are exactly the same results for the dot plot. It's another way of representing the same information. It's again accuracy and kappa.
We have just scratched the surface in terms of the different functionalities that the correct package offers. The correct package is huge. It really has different types of functions that you can use, and I really encourage you to explore the documentation that I'm putting here, because it will allow you to explore different functions and different examples that I haven't had a chance to show you in this class, but that I think would be extremely useful for your milestones. So again, make sure that you go through this documentation and familiarize yourself with the many other things that can be done with this package.